All righty, so let's do a quick series review. All right, so we talked about a sequence. A sequence is a list of numbers. It is separated by a comma. We can determine the limit of a sequence. The series is a sum of the terms of a sequence. We can determine the sum of a series if it converges. For a sequence, an of numbers to converge, we look at the limit of the nth term. If it equals a number, then the sequence converges. If it does not, it diverges. For a series, we look at a sum of the terms in a sequence, and it has to form summation n equals 1 to infinity of an. And then we can find the sum s, which is the sum from n equals 1 to infinity of an. If we get a number, the series converges, otherwise it diverges. Okay, so we talked about 12 tests. All right, so I can't fit them all in the screen, but I can get most of them there. Okay, so we had the geometric series test, the telescoping series test, the nth term test of divergence, the integral test, the p-series test, the direct comparison test, the limit comparison test, the alternating series test, the test for absolute convergence, the test for conditional convergence, the ratio test, and the root test. Of these series tests, only 2, you can actually find the sum of the series. Only 2 of them can you find this actual true sum, and that is if they are convergent. All right, then these tests, which is all of them with the exception of 1, determine whether a series converges or diverges. The nth term test of divergence does not determine convergence. It only tells you if the series diverges or the test is inconclusive. Okay, any questions? We've gone through all of these tests in detail. I will have a quiz for you guys on Thursday. All righty. Since there are no questions, let's move on.
Sorry, what you say?
What did I say about what? I said a lot. What do you mean?
You said something on Thursday.
Oh, Thursday, I said I'll have a quiz for you guys that we'll do in class.
Can you scroll down a little bit, please?
I
Like a
certainly.
Kahoot?
Pardon? Yeah, similar to a Kahoot, yes. Or a, it'll either be a Kahoot or it'll be a PowerPoint, like I did one of those 2 times, yes.
Okay.
So, well, this is it like a graded quiz or just like a quiz to see what we know?
This is a quiz
At this
to see what
point.
you know. Yep, quiz to see what you know. Okay, any questions? All right, thank you guys for paying attention. Okay, let's go to module 8. All right, so module 8 has 3 sections, and then at the end of next week, we are done. All right, so in module, this module, oh, I'm on the wrong day. Here they say that's not what we're doing today. Okay, we're introducing power series, and we are going to identify a power series and provide examples of them. We are going to determine the radius of convergence and the interval of convergence of a power series and use a power series to represent a function. Okay, so I'll give you a few seconds to write this down. This is the form of a power series. All right, it is the sum n equals 0 to infinity of Cn x minus x naught to the n. Okay, couple things that you need to know about this power series. The first thing is this whole thing is my an. Okay, second thing you need to know, Cn depends on n. And x naught is a real number. It can be anything. Okay, X naught is a real number. All right. First example. So the first example is X naught is going to be 0, and our Cn is simply equal to 1. All right, so this series, the Cn collapses because it's a hidden 1 in front of it. And then the X naught is actually X minus, so this is the sum, n equals 0 to infinity. Stop it. And then we have a silent 1, and then we get X minus 0 to the n. So the 0 collapses, so we just get that. Okay, any questions? All right, so the first term is X to the 0. The second term is X to the 1. The third term is X to the 2. And we just keep adding these terms and we end up with this series. Okay. All right, so that's the first one. Number 2. Okay, so in the second power series, we're going to again let X naught be 0, but this time my Cn, oh, this is missing the X to the n. How did I do that? This is X to the n. Uh-oh, no, not theirs. Good, X to the n. All right, now it's power series. Okay, I was missing this. Notice that these power series are functions of X. Okay, so here's my Cn. Here it is.
Look.
Okay, so it is Cn X minus 0 raised to the nth power. Okay, any questions? All right, so when I put in n equals 0, I just get x minus 1 to the 0, xn to the x to the 0, and oh, I got 0 in the denominator. Well, actually, I don't. We got to remember that 0 factorial is 1. And so once we remember that, we don't have a problem. So 0 factorial is 1, so we get 1. For our second term, we get minus 1 to the first power, because n is 1 there. And then we get x to the 1 over 1 factorial plus x squared over 2 factorial minus x cubed over 3 factorial, etc. Okay, so this is our second power series. Any questions about this one? Okay. All right, so our third example, this time we have x naught is equal to 2. So I have x minus 2 to the n. And then my Cn is 1 over the square root of n plus 1. So this term is when n equals 0. This term is n equal 1. This term is n equal 2. This term is n equal 3, etc. Okay, any questions? Okay. So some power series converge to a number or a function, and some will diverge. Just like our regular series, some will converge and some will diverge. Okay. So let's start. Let's get started. Here's our first one. This one is the most important of them all. Okay, so the first one is, we looked at this a minute ago. The sum n equals 0 to infinity of x to the n. I can rewrite this conveniently as the sum n equals 1 to infinity of x to the n minus 1. It is the same series, but now is in a different form. Can anybody tell me what type of series that is?
Geometric.
It is a geometric series. Fantastic. Okay, so we have a geometric series. It looks weird, but it is a geometric series. A is 1, and here R is x. We're used to seeing a number there, but R is x. It's actually x minus 0, but R is x. And we know that this series, this geometric series, converges. So this geometric series converges under what condition? Let's say only if.
One
Only
of the worst times.
He went to lot after all.
Is it if the absolute value of it is less than 1?
good. So the absolute value of R
Guess
is
what,
equal
freshies?
to 1.
Hey,
Next semester,
No, go
I'm
ahead.
doing a mobile computing course. Doesn't even look like a float.
Muted?
He's not listening.
I don't understand y'all. Y'all can be, I don't get it. If you're not going to pay attention to the lecture and do something else, at least do it quietly, please. The geometric series converges only if R is less than 1. Thank you, Devin. Okay. And when R is absolute value of R is less than 1, we know that this series then, so it converges to the sum, which is 1 over 1 minus R. And Benaya, I'll change your attendance. So it converges to 1 over 1 minus R. Okay. I'm sorry, A over 1 minus R. I'm saying 1 because I already know A is 1, but it converges to A over 1 minus R. Okay, so that means we can say the summation n equals 0 to infinity of x to the n is the summation n equals 1 to infinity of x to the n minus 1. And that's going to be 1 over 1 minus R, which is x, only if the absolute value of x, which is R, is less than 1. Okay, so we now have our very first function that is being represented as a power series. So we can now say that f of x which is equal to 1 over 1 minus x, is actually equal to the sum n equals 1 to infinity of x to the n minus 1 if the absolute value of x is less than 1. Okay, so that power series not only converges, it has a sum. We can represent it as a function. Okay, so I would very much like it, which it has not been doing. I don't know why it won't do it, but yeah, it's not doing it. It's making me angry. Okay, there we go. All right, so that was the first example. Let's go to the second example. Okay, now this one is a lot more fun. All right, so we want to know, so we already know for the power series above that it's only going to converge if the absolute value of x is less than 1. We already know that. Okay, so it converges on the interval -1 less than x less than 1. We're going to actually give that a name. That is the interval of convergence, and we'll be finding it for the other ones here. And the radius of convergence for this one is just going to be 1. And we'll talk about that for the next example. Okay, so we have the summation -1 to the n of n factorial over x to the n. Okay, so now I need to determine where or when this power series converges. So determine where, on which interval does this power series converge. Okay, so that's my task. All right, so now when we check to see whether series converge or not, we use certain tests. So I'm going to give you a hint here. My AN is -1 to the n times x to the n over n factorial. Now, if that is my AN, what test am I going to use to determine whether or not the series converges?
This is the ratio test.
I am going to use the ratio test. Thank you very much, Rodney. All right, so as we can see, I want to go to here. For the ratio test, first off, it says the root test, never use it for factorials, but we already know here for the ratio test, it is the best test to use for factorials. Okay. So oh, I see what I did. I mixed up my lecture here. So I am actually, alrighty. So I just have to switch those. That's fine. All right, so we're going to use the ratio test. And we're going to put an exclamation point because we're excited about it. All right, so with the ratio test, we have to compute rho equal to the limit as n approaches infinity. And then we're going to need to find the absolute value of an plus 1 over an. So we'll compute that. And then what do we know about the conditions for the ratio test? When does a series converge when we use the ratio test? So after I go through all the work to do the limit as n approaches infinity of the absolute value of an plus 1 over an, and I get rho, what do I check? Okay, come on, guys. We check to see if the row that we got is less than 1, and then if it is, our series converges absolutely. We check to see if our row is greater than 1, then we know it diverges, and if row is equal to 1, the test is inconclusive. So we do not want the series to diverge, nor do we want a situation where we've done this and our test is inconclusive. We want the case when row is less than 1, then we know our series converges. So we're going to compute row, and then we are going to find when row is less than 1. I should say where. Okay, so then we will find where row is less than 1. Okay, so let's compute row. So let's scroll back. What is an plus 1? Somebody help me, please.
Is it -1 n, well, to the n plus 1, and then x, and then to the n plus 1 over n plus 1 factorial?
That's right. Okay, so that is our an plus 1. So now our row is the limit as n approaches infinity of, we're going to take the absolute value. So when I take an plus 1, I'm going to get -1 to the n plus 1 times x to the n plus 1 divided by n plus 1 factorial. Uh-oh. And when I divide by an, that means I'm going to multiply by its reciprocal. So I'm going to get n factorial in the numerator. And then I'm going to get over. And in the denominator, I'm going to get -1 to the n times x to the n. Okay, any questions about that? Okay, so now row is going to equal the limit as n approaches infinity. And now the -1s inside are going to, in absolute value, they'll be gone. Because when we take the absolute value of -1, we're going to get 1. Then I'm going to take the x to the n plus 1 over the x to the n, and that's just going to leave me an absolute value of x. And then I'm going to take n plus 1, well, n factorial over n plus 1 factorial, and that is simply going to give me n. And when I take the limit of that as n goes to infinity for any x, I just get 0. So 0 is always less than 1, always, always. So for this one, this is always true. So that means this thing is actually going to converge for all x. It converges everywhere. All right, so this converges. For all x. Okay, so we want to write this out. So we can say now that the radius of convergence, that means how far does it converge from 0? Well, that is just infinity. It converges for everything. So the radius is infinity. And then the interval of convergence well, that's just going to start at -infinity can go all the way up to infinity. And remember, our x naught was 0, so we're looking for a radius or an interval about 0. So we got that whole thing. Okay, any questions? Our next one is the most fun. Well, actually, the next two are the most fun. I think they're awesome. Okay. So this one says sum n equals 0 to infinity, minus 1/2 to the n, x minus 3 to the n. So when I look at an turns out to be negative 1/2 times O to the n times x minus 3 to the n. So a couple things that we know first. Cn is simply negative 1/2 to the n. Our x naught is simply 3. So we're going to be looking for a radius about x equals 3 to determine where this thing converges. Okay, so we get that much, that far. Okay, so now for this problem, we have a choice. One, we can use the root test. And two, we can use the ratio test. Now, I actually, for this problem, I'm going to go ahead and use the root test and both of them will give you the same answer, but I'm going to use the root test because everything in here is raised to the n power. So for the root test, we take the nth root, so that's going to be easy. Okay, so what happened with the root test now? Well, for the root test, here we are. So for the root test, we're looking for rho to be the limit as n approaches infinity of the nth root of the absolute value of an. And then after we compute that, we want to look for where rho is less than 1. Okay, so we're going to compute rho. The limit as n approaches infinity of the nth root of the absolute value of an. Now we can also write that as the limit as n approaches infinity of the absolute value of an raised to the 1 over n power. And that's the form I like to use, and that's what I'm going to use. All right, so let's compute rho. All right, so first off, the absolute value of an is the absolute value of minus 1/2 to the nth power times x minus 3, also to the nth power. So I can pull the absolute value inside. And so I just get 1/2 to the nth power times the absolute value of x minus 3 to the nth power. So I know what the absolute value of an is. So rho is the limit as n approaches infinity of the absolute value of an raised to the 1 over n power. So that's the limit as n approaches infinity. We have 1/2 to the n times the absolute value of x minus 3 to the n, all raised to the 1 over n power. And when the 1 over n power hits that, I just get rho is the limit as n approaches infinity. I get 1/2 to the n gives me 1/2. And then absolute value of x minus n to the n to the 1 over n just gives me the absolute value of x of minus 3. And when I take the limit, there is no n, so I just get 1/3 the absolute value. Oh, no, I don't. I get 1/2. Uh-oh, come on now. Okay, now we already know that using the ratio test and the root test, it only converges when rho is less than 1. So this converges only if rho is less than 1. So that implies for us 1/2 times the absolute value of x minus 3 is less than 1. And when we multiply both sides by 2, we get the absolute value of x minus 3 is less than 2. And that is our very nice radius of convergence. Okay, it's the radius of convergence because I'm able to say the absolute value of x minus x naught is less than r. So that's my radius of convergence. Now I need to find my interval of convergence. That means for what values of x will this actually converge? And when I go to do that, I first find what I call a preliminary interval of convergence, because we still have to check endpoints, because this only gives us up to a certain value, but doesn't include the endpoints. So now I get -2. I want that black. I get -2 is less than x minus 3 is less than 2. So this gives me 1 is less than x is less than 5. And so this is my preliminary interval of convergence. Okay. All right. So I kind of have an idea that it definitely will converge if x is greater than 1 and less than 5. But I don't know if it converges at 1 and at 5. Okay, so the question now is, does the series converge when x is equal to 1 and 5? So those we have to find out. Okay, so how do we do this? So we need to check those. So let's go back to what our series was. So let's let x equal to, so if x is equal to 1, what do we get? This is equal to the sum n equals 0 to infinity of -1/2 to the n. I'm going to put 1 in for x, so I get -2 to the n. So this gives me the sum n equals 0 to infinity. When I take -1/2 and multiply it by -2, I just get 1. So this looks like 1 to the n. And 1 to the n is just, for us, we're just summing this up. Okay. All right, so this series just adds up 1, just 1 plus 1 plus 1 plus 1 plus 1. Okay, so this series diverges. So let's look at the nth term test. we know n to 1 to the n, literally for us, for the most part, is simply just 1. Okay, so there, an is equal to 1, which is not 0. So this series diverges. So now we know the series does not converge at x equals 1. So now let's look at x equal to 5. Okay, so for x equals 5, we get the sum, n equals 1 to infinity. I'm going to get negative 1/2 to the n, and I put in 5. That's going to give me 2 to the n. So now I'm going to get minus 1/2 or negative 1/2 times 2. That's going to give me negative 1 to the n.
I know everyone
Dr.
has
Lara?
that problem.
Yes.
Why did you start with n equals 1 this time?
Because it should be 0. I'm so used to writing 1. Yep, it should be 0. Thank you. All right, and so the limit, this term, the diverges. All right, so the limit n approaches infinity of minus 1 to the n, this thing diverges. So by the nth term test of divergence, this does not converge. All right, so we can say the series all right, so therefore, since we know it doesn't converge at x equals 1 or x equals 5, we can write the following. So we can conclude that the radius of convergence is equal to 2. And the interval of convergence that's equal to 1, 5. So that's it. Any questions?
It varies
was
a
the
lot.
conclusion
Like, you
again?
gotta look at.
Okay, I got 2 questions. What are you saying?
What was the conclusion again? Oh, sorry. I see
The
that.
2 conclusions that the radius of convergence is indeed 2, because we had here x minus 3. So with the radius of a convergence, you get x minus x naught is less than r. So in our case, x minus 3 is less than 2. And then your interval of convergence comes from solving the absolute value and then checking the endpoints. And for us, the endpoints did not converge, so we can't include 1 and 5. Okay. All right, next problem. Okay, so this next problem is certainly a lot of fun. Okay, this one is a lot of fun. All right, because this one involves everything, and those are the good ones. And we only have 20 minutes to do it in. Okay, all right, let's get moving. All right, so let's look at this. Our X naught is 0 because it's X to the N. Our Cn is 1 over n, the square root of n times 3 to the n. So that's Cn, okay? And our An, that's the whole thing, is X to the n over n, oh boy, the nth root of n. Nope, that's wrong. It's the square root of n. Times 3 to the n. So once again, I have a choice. So we can do 1 ratio test or 2 the root test. All right, I have a preference. I'd like to see what other people think about this. What would you do? What would you do?
Use the root test.
I would use the root test as well. Okay. All right, so for the root test, rho is the limit as n approaches infinity of, we already said it was the nth root of the absolute value of an, or we could write this the absolute value of an to the 1 over n. So I'm going to use that one because I like that one. Okay, so the absolute value of an, well, everything is positive except for the x. We don't know about the x. So we have to have absolute value of x to the n because x may not be positive. But in the denominator, we have n. I'm going to write this as n to the 1/2. And then I have 3 to the n. All right, so that looks good to me. All right, so rho is the limit as n approaches infinity. And I'm going to take this whole thing, absolute value of x to the n, divided by n times n to the 1/2 times 3 to the n. And I'm going to raise that whole thing to the 1 over n power. Okay. All right. Anybody want to simplify this for me? Anybody want to simplify this for me? I have x to the n to the 1 over absolute value of x to the n to the 1 over n. What is that going to give me? The n to the 1 over n goes away, guys. Okay. Then I have n to the 1 over n. I have n to the 1 over, this is 1/2, not 1 over n, that's n to the 1/2. So I have n to the 1/2 to the 1 over n, and then I get 3 to the n to the 1 over n just gives me 3. So that's it. And I still have to take a limit. Okay, so the two things we need to recall. The first thing is that the limit as n approaches infinity of n to the 1 over n is what? What is that limit? That's one of the ones you have to remember. You have to know in order to do these problems. What is that limit? Hello? Okay. And n to the 1/2 to the 1 over n is the same as n to the 1 over n to the 1/2. We can do that with powers. Okay, so rho then is the limit as n approaches infinity of the absolute value of x divided by n to the 1 over n to the 1 over n to the 1/2 power times 3. So this limit becomes the absolute value of x over 1 times 3. So I get the absolute value of x over 3. All right, so now I have done the root test and I have found rho. All right, so this series converges. Only if rho is less than 1. So that then implies that the absolute value of x over 3 is less than 1, or the absolute value of x is less than 3. Well, there we have it, the radius of convergence. So this is the radius of convergence. So that means on an interval about x naught, which is 0, I can go up here and down here. So this is -3 and 3, and the radius is 3. So easily I can see the interval of convergence. I should say the preliminary. Well, that's just -3 to 3. All right, so I have -3 less than x less than 3. So that's the preliminary. All right, so now we need to check our endpoints. So now we have to check our endpoints. So let's let x equal 3. And bring back the original series. One of my favorites. Okay. So if x is equal to 3, sum equals 1 to infinity, I'm going to get 3 to the n over n. And I'm just going to write this as n to the 3/2. And then I get 3 to the n. And notice the 3 to the n's divide out. Wow, look at that. and this is the sum, n equals 1 to infinity of 1 over n to the 3/2. Oh my, what kind of series is that?
Is that a P series?
That is a P series. Thank you, Lawrence.
You're welcome.
This is a P series. What is P?
3/2.
Does the series converge or diverge?
Converges.
Yes. Okay, so that series converges. So that lets me know that this series converges for x equal to 3. So I can include 3 now. Okay. Now we got to check x equal to -3. So let's bring the original series back again. So put in x equal to -3. So I get -3 to the n divided by n to the 3/2 times 3 to the n. And the 3 to the n still cancel again, but the -1 to the n stays. Okay, so now this is not a P series anymore. It has a name. What is it?
Oh, God.
Wow. It's an alternating series. -1 to the n automatically says that's an alternating series. So I can use the alternating series test. So 1 show by the alternating series test. That's the first way we can do it. Okay. And 2, we can say this converges absolutely by the test for absolute convergence. And the reason why is because we already showed that the absolute value of this converges, right? So we showed that the sum n equal 1 to infinity of the absolute value of -1 to the n over n to the 3/2 is equal to the sum n equals 1 to infinity of 1 over n to the 3/2 converges. We showed that. So that implies then that the original series minus 1 to the n over n to the 3/2 converges absolutely. Okay, so now we can say the series converges at x equal to minus 3. All right, so now we have to redo our interval of convergence. So our radius of convergence, so we can now conclude radius of convergence is clearly equal to 3. Nothing changes for that. But now the interval of convergence now let's see. Originally, our preliminary, we knew it converged from minus 3 to 3, right? But now we just checked 3 and minus 3, and we know it converges. So now I can put negative 3 to 3. So that's the whole interval. Okay, so that's it for that problem. Any questions? Fine. So, expansion. Equaling 1 over 1 plus x, 1 minus squared. Okay. So you will be asked to find a power series expansion for something using something you already know. Okay. So we already know the power series expansion for this. Okay, so we know the power series expansion for that. So therefore, we just get that f of x well, let's see. Here, we have an x, 1 minus x, and that's x to the n. So now I have 1 minus x squared. So that's going to be the sum, n equals 1 to infinity. I'm going to put an x squared there because that's what it has to be, to the n minus 1. So I get that. And lastly, f of x equal to 1 over 1 plus 3x. Well, instead of x, I'm going to put minus 3x. That's the sum, n equals 1 to infinity. I get negative 3x to the n minus 1. So this one converges for the absolute value of x less than 1. This one's going to converge for the absolute value of minus 3x less than 1. So x is going to have to be less than 1/3. Okay, that is it for today. I will see you guys on Thursday, unless you come to office hours this afternoon or tomorrow morning. All righty, have a great day and a great Wednesday.
Dr.
Like, you already